All right. Good afternoon, class. Good morning, good night, whatever time it is. This is our day 15 lecture video. So we've just finished test two, and now we are ready to start into a new chapter. So we're going to look in chapter six for today's video, as well as tomorrow's lecture video. We're going to finish up chapter six here, as it's kind of a shorter chapter, and then we'll be able to get into some of the bigger chapters to wrap up this course. All right. So chapter 6, we are looking at sections 6.1 and 6.2 today. So I'll go ahead and share my screen. For day 15, we're going to start in chapter 6. We want to start examining something called a sampling distribution, where basically the idea at this point, we understand from statistics that whenever we're trying to estimate something in the real world, then we need to take a sample. We have to collect a sample in some way. And our hope is that our sample is going to be somehow like a picture or a similar picture to what is happening in the larger world or in the overall population. All right. Now, unfortunately, a sample might not always be accurate or it might be biased in some way. And so by looking at sampling distributions, this gives us a way to try to level out that possibility for a sample to be wrong. All right, we're going to look at that today as we start into chapter 6. So for section 6.1, I'm just going to start here on the whiteboard. So I'm going to go ahead and turn off my screen share. And we're going to start with a random variable, which we're already familiar with. So it'll be kind of a nice example to start with, where consider rolling a six-sided die, right? If we have an experiment where we roll a fair six-sided die. Okay. Then the value of the die after it's rolled, in other words, our random variable x, can be 1, 2, 3, 4, 5, and 6. And for any one of these guys, because this is a uniform distribution, this is a uniform random variable where each output is equally likely. Each value of x is equally likely. And so for any little x in capital X, the probability of that little x is 1 over 6. All right. So this is a random variable that we're familiar with. And if we're thinking about in terms of what's the population here, the population is all the possible dice rolls that could possibly ever exist. If I were to roll a six-sided die a million times, a billion times, all the times that these dice get rolled in the world all over. Okay. Well, then, on average, what do I expect to get from these dice? Well, okay, this is a bit of a redundant question in some ways because, well, it's equally likely to be anything from 1 to 6, right? But we can still find and calculate an expectation. We can still determine, well, what is the average here? After all, if this is like a uniform distribution, then on average, I'm going to have values somewhere in the middle, right? It can be equally likely 6 or 1. But at the end of the day, as I have this spread from 1 to 6, on average, if I'm like thinking about a max minus a min divided by 2, like we've previously seen with uniform distributions, then on average, somewhere here in the middle, okay? But we have a formula for expectation. This is coming to us from, to back up for a moment, we covered this in chapter 4, where the expected value of a discrete random variable could be calculated by summing up each x multiplied with its respective probability. So you might recall doing this, I guess this would have been a couple weeks ago, maybe, or actually a week ago for this class, since it's since this is a faster paced class. Um, this was our formula we used for calculating expectation, or in other words, finding the average, where in this case we're talking about the average for the population of all possible die results from a six-sided die. Okay. So we can put this into our formula. I'll have 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. Okay, well, then what do we get here? I have 1/6 plus 2 over 6 plus 3 over 6 plus 4 over 6 plus 5 over 6 plus 6 over 6. So this will be 1 plus 2 is 3, plus 3 is 9, plus 4 is 13, plus 5 is 18, plus 6 will give us 24. And so we have 24 divided by 6. Wait, hold on. I feel like I added something up wrong here. What did I do? Going to the calculator. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Yeah, I did. I made a mistake here. You probably already caught this. If you're adding up all of this, this is supposed to add up to 21 over 6. All right. Or in other words, 21 divided by 6 is 3.5. Which, yeah, okay, just like we were talking about, in terms of what is the dead middle between 1 and 6, 1 plus 6 is 7, divided by 2, we get 3.5. So no surprise, we find out that the average here is 3.5, okay? So this is a population where we already know what the population average should be, given, if I am able to calculate this expectation for larger and larger populations based off of these probabilities. Okay, we saw this in chapter 4. But suppose for a moment I didn't know the average was 3.5. In the real world, how am I going to study a population? I need to collect a sample, and then I'm going to look at the average from that sample, and hopefully, maybe it's close to it. Okay, so I'm going to make a note up here. First of all, we already know that the average for this random variable is 3.5. Okay. Well, let's back up. Let's say that now, suppose I didn't know that, and we take some random samples to see what the average is. All right. And so maybe I have one sample where, and this is coming to us from section 6.1. So maybe I have one sample where I'm going to roll the die 3 times. So roll the die 3 times. And I get a sample where I have 2, 2, and 6. All right. Now, sure, we might already be thinking to ourselves, well, wait a moment, a sample size of 3, that's pretty small. That can't be large enough. And yeah, you're right. In the real world, we'd probably try to use a larger sample to try to approximate what's happening. But this is just for the sake of the exercise here to kind of get a feel for what's going on in chapter 6. Okay. Now, if I try to find an average here, well, then this is a sample average. So I'm using x bar instead of the Greek letter mu. This is a sample average. I'm going to use subscript 1 here to indicate this is the sample average from sample 1. Well, add it all up, divided by 3, and we're going to get here 2 plus 2 plus 6 divided by 3 is 3.33. Which, okay, at the end of the day, that's not too far off from what the average is supposed to be, so it's not bad. Another option would be, well, what if I want to use a median to try to approximate what the middle for the sample is, right? After all, we can use an average. We can also use medians to try to approximate a middle. Then for the median, I would get 2, which, all right, yeah, the average is definitely a closer method here, at least for this sample. Okay. But let's suppose I take another sample. I have sample 2. I roll the die 3 times. This is a different sample. And for this sample, we get 3, 4, 6. 3, 4, and 6. All right. Well, now the average for my second sample will come out to be added up and divided by 3. We'll have 4.33, and we'll have a median of 4. Now, if I didn't already know that the middle, the average, is supposed to be 3.5, how would I know which sample is giving me a better estimate here? I mean, for sample 1, the average was closer. But for sample 2, the median was closer. So in general, if I don't know, what am I supposed to do? Do I use the average? Do I use the median? How do I know if I have a good estimator? How do I know if my sample is actually close to the real thing that's happening in the larger population? Or is my sample just a weird dumb luck thing where it just turned out that I got larger numbers and the average is not actually that high? All right. So in the grand scheme, what do we need to do? Well, partly what we're getting to is that one sample is not necessarily enough, in which case, maybe we want to take many samples and then average over all of those samples to try to create a more holistic picture of what is actually happening here. Okay. So that's kind of where we're going with chapter 6, where a sampling distribution is this idea of, well, what if I take a sample and then take a second sample and then take a third sample and then take a fourth sample and a fifth sample and a sixth sample, so on and so forth, where each one of those samples might be close to the real population data or it might be far off from the true population data, just due to dumb luck. All right. And so to try to compensate for that, instead of looking at a single sample, we'll take a bunch of different samples and then we can kind of average over all of those samples to try to get like a more accurate picture. Okay. So that's our goal here as we're continuing in chapter 6. All right. Now, similarly, what we're doing here is we're trying to estimate a population average. Now, in the case of this example, we already knew what it was, right? But oftentimes, we may not know what the true population average is, and we're just having to make an educated guess, all right? Now, in terms of probability, we're still going to do this the same way as we did in chapter 5, or at least mostly the same way. Later in chapter 6, when we cover 6.3 in the next video, we'll find out that z-scores are calculated slightly differently for a sampling distribution, but otherwise it's the same kind of formula, it's the same kind of process. So we'll see that more actually in the next video, not in this one. So let's look at another example here. How is this similar to what we did in chapter 5? Well, suppose I have a population average of 10 with a standard deviation of 5, right? So I know my population data should look something like this, with 10 here in the middle, and then I can kind of branch out to the left and right. All right. But suppose I didn't know this, all right? So cover this up for a moment. Suppose we didn't know the population information, then we could take samples to estimate the average, right? If it is not known, which again, most of the time, it isn't known. And so this is kind of our hope that we're going to take some samples and try to use that to estimate what's happening here. All right. And so, if I have a sample size of 25, so n is 25 here, and then we get some x bar from the sample, whatever sample we collect, all right? Now, when it comes to the question of how do we talk about probability, it's still the same idea, except now we're talking about a sampling distribution average. We're asking about the probability of what is the average. Instead of saying the probability of X, we're looking at what is the probability that the average is, for example, between 9 and 10. Well, then my sampling distribution, this is a normal distribution, hopefully. But now this is a distribution of averages instead of a distribution of x's. So I want to make clear the difference here. This is a distribution of, wait, hold on a moment. That should be 11. All right. This is a distribution of averages of x bars instead of x's. Okay. And so to find this probability, well, it's the same idea as before. I need to know the area under the curve for this region to find that area, or to find that answer, that probability, all right? Now we would still, just the same as we did in chapter 5, we'd want to rewrite this as a question about z-scores. However, z-scores are calculated a little bit differently. I don't want to go into the details of all that in this video. Again, that's going to be in the next video. That's covered in section 6.3. But I just kind of want to tease where we're going with this and how this builds off of what we already did in chapter 5. All right. So to kind of bring this a little bit clearer, I want to go back to the textbook now. And we're going to look here at... This is example 6.3 in the textbook. So I'm going to share my screen. Share my screen. Okay. So we're looking at example 6.3 from the textbook, where in essence, part of the purpose of this sort of question would be, for example, in a factory. In the case of this problem, we have a rolling machine of a steel manufacturer which produces sheets of steel of varying thickness. The thickness should follow a uniform distribution, so assuming the machine is working correctly, that's kind of the key here. As we continue to chapter 8 and chapter 8, or chapter 7 and chapter 8, we're going to be talking about questions of how to test if a machine is working correctly or not. We have to statistically determine if a machine needs to be recalibrated or fixed or replaced. So that's where statisticians, as well as engineers, kind of come together on this sort of question to help manufacturing as a whole. All right. But if the machine is working correctly, it follows a uniform distribution. So they gave us this picture to the left of this uniform distribution where the thickness ranges from 150 millimeters to 200 millimeters. All right. And if the machine is working correctly, it's supposed to produce steel always in a range of thickness from 150 to 200, equally likely any of those numbers. All right. Now they're trying to determine, is this true? Is this correct? Is the machine working correctly? Right? We already know for a uniform distribution, we can find the average by taking the maximum minus the minimum divided by 2. So we know the average should be 175. All right. On average, the sheets of metal should be somewhere around 175, maybe a little less, maybe a little more. But most of the time, they're going to be somewhere in the middle. Okay. So how do we find out if the machine is working correctly? We collect samples. So for this experiment, again, randomness is important for a sample to be trustworthy. We randomly sample 11 steel sheets from the production line and record the thickness of each. So we collect a sample, we measure their thickness. Do that for the entire sample. So X bar is the sample average, this average divided by 11, since that's the sample size. The median, well, that's whatever the middle is of these 11 data entries, in which case that is going to be the sixth sample measurement when the 11 different entries are arranged from least to greatest, all right? So that's how we can calculate the median. And then they're going to repeat this. They're going to repeat this process. In this case, they're doing this with a computer to kind of randomly simulate what's happening here, where we're going to take a sample 1,000 times, and each sample has 11 sheets of steel, which are randomly selected. Okay? So this data is represented here. Um, and they show us the first 10. So they're not outputting all 1,000 samples. These are just 10 of the samples. Each sample has 10 different data entries which have been collected. So these are 10 different X's for each sample. Or sorry, 11 different X's since the sample size is 11. Then for each sample size, we calculate an average. That's the X bar. And I have a different X bar for each sample. I'm also getting different medians for each sample. And yeah, we see a lot of these are kind of close to 175. Some are a little bigger, some a little less. There's some variation here. This is kind of the approach, the idea, the theory behind sampling distributions. Okay? So they then create this histogram, right? Since after all, we can use histograms to represent population data, where hopefully, if we're lucky, it'll be kind of like a normal curve shape where we have this hill shape there in the middle somewhere. Okay? And so the height of the bar is representing the frequency. How many times did that average appear? And so it looks like in this graph, 174 appeared the most times. We also have this other bar next to it that's pretty high, somewhere between 174 and 180. Maybe that's like 176. I'm not sure what the scale is here exactly. This is what's happening here, right? We have some samples where just due to random dumb luck, where the average might be really low, like 162. Some of them, again, just a dumb luck, might have a sample where the average is really high, where this one, it looks like it's like 188, 190. That's a pretty high average. But we see these higher frequencies are gathered in the middle. Most of my samples are having an average somewhere in the middle. And so this is what we want to do with the sampling distribution. Take a bunch of different samples. We have a bunch of these different X bars, and then look to see, well, where are these X bars gathering to try to figure out where is that clustering in order to determine what is the true population average. Now, if I had clustering which was like around 140, or maybe it was like 220, then we would know, well, wait a moment. This machine is supposed to produce steel between 150 millimeters and 200 millimeters. If I'm getting an average with a high frequency that is way off, that's telling us there's something wrong with the machine, right? Which on this kind of scale, millimeters, we might not be able to tell with the naked eye. I mean, a millimeter is not that big. Um, but with measurements, with statistics, we're able to detect what might not be perceptible just by looking at it. All right. So this is the idea. This is what we're trying to do in chapter 6. Okay. So let's go look at section 6.2 now, where, what makes for a good estimate or what makes for a bad estimate. Now, theta, what they're representing here in the pictures, and I'll put this on the board behind me in a moment. Theta is some parameter, some statistic that we are trying to estimate about a population. Usually, for our purposes, theta is going to be the mean. It's going to be the Greek letter mu. But when it comes to a population, there might be lots of things we're trying to measure. Look here in the problem. Note that theta could be any parameter. It could be the mean, it could be variance, it could be the standard deviation, so on and so forth. Whatever it is we're trying to estimate about the population, we need to use some kind of statistic to estimate that. All right. Now, how do we estimate the average? Maybe not so much a surprise here, but oftentimes to estimate the average, we take X bar. We find the sample average to estimate the population average, which Makes sense to do since it's the same kind of calculation. But we don't necessarily have to do that. We could use different methodologies for calculating the average or trying to find that middle, right? Since both the average and the median are supposed to be in the same spot. But unfortunately, different methods don't always work as well. So we might have a method A where I am using the average of the sample. I'm using X bar to approximate the population average. But then method B, maybe I'm using a median. Maybe I'm using some other method I've come up with to try to estimate whatever theta is, trying to estimate the population average, okay? Now, how do we know whether or not we've done a good job? Well, if our methodology is an accurate methodology, then wherever we have our peak and our frequencies, so we said in the picture here, so for A here, this is a good model because, well, theta, which is the population statistic that we're trying to estimate, it's here in the middle where we have this highest frequency. That's a good estimator, right? They match up, they line up. This then should be a trustworthy method for determining whatever theta is about the population. But if my methodology is giving me a frequency somewhere else, or it's giving me this big peak at a different location from where the true population average is, then that's where we have a biased statistic. This statistic B is not actually lining up with theta that we're trying to estimate. And when these two things do not line up, then that is considered a biased methodology. That is a sampling statistic that we do not want to use. All right. We want to be as close to the real, true population average as possible. We want to use methodologies which are accurate in order to do that. Okay. So how do we know what's trustworthy or what isn't trustworthy? We can do some testing. Now, example 6.5, they've created these distributions based off of the gambling game for craps. And I don't want to go into all the details of how the game works and how the probability is calculated for this, but this does allow us to jump into today's participation question. All right. So this is participation day 15. And I'll make the screen a little bit bigger here. And essentially what's happening here is that we've created two different sampling distributions. We're trying to estimate the population average in this situation, okay? We have X bar, where these are different sample averages we've seen. There's -5, -3.33, -1.67, so on and so forth. These are different X bars, which have their own different probabilities, right? So if this is like a, like a bell curve shape, then I've got these higher probabilities, this higher frequency around 0 and 1.67. And then as I go to the left, as I go to the right, that frequency starts to come down and starts to be less common. It has a lower probability, okay? So we're trying to estimate the population average, and we have this sampling distribution, which is using X bar. We also have this other sampling distribution, M, which is using the median. And so these are two different distributions, which are calculating different results, trying to determine what is this kind of middle value, okay? Now, suppose we already know that the population average is 0.54. Which distribution is a better estimator for the mean? How do we know? Well, in either case, these are random variables, right? This is the random variable X bar, and this is the random variable M. We want to know which one has an average which is closer to the true average we're trying to get. All right. So you can go ahead and have this on a different screen, save this, take a picture of it. We're going to use this on the whiteboard behind me. So I'm turning off the screen share, right? And so what we want to do is determine the expectation for these two different sampling distributions and see which one has a sampling distribution closer to what we're actually looking for. All right, so we're using the exact same formula for expectation that we saw from earlier, where the expectation of x bar. So I'm trying to find, well, what is the average I would expect to get from this x bar sampling distribution? According to our formula, I need to sum up the x bars multiplied with their respective probabilities. Okay? Well, for x bar, we have, now I'm reading from the table, which is in the exercise in Canvas. I have -5 with a probability of 1 over 729 plus we have -3.33 with a probability of 18 over 729 plus -1.67 with a probability of 114 over 729 plus we have an x bar of 0. Well, that'll just be 0 times the probability, so I don't have to write that out. That'll just be 0 plus 1.67 with a probability of 228 over 729 plus 3.33 with a probability of 72 over 729 plus 5 with a probability of 8 over 729. All right, so I'm just using the same old expectation formula that we had from chapter 4. Take each x bar, multiply it with their probabilities. I've got, let's see, -5 over 729 plus, let's see, -3.33 times 18 over 729 plus -1.67 times 114 over 729 plus 1.67 times 228 over 729 plus 3.33 times 72 over 229 plus 5 times 8 over 729. Let's see, did I type this all in correctly? -5, -3 here, -1. Um, 8 over 729. Let's see. I feel like I have a typo here. I copied something wrong here. -5 times 1 over 79 plus 3.33 times 18 plus -1.67, 114 over 729 plus the 0 plus 1.67, 3.3 times 72 over 729 plus 5 times 8 over 720. Okay, Yeah, I made a little mistake when I was typing this in on my phone. But the result here is supposed to come out to the expectation of x bar is 0.556. All right. So there's at least we're part of the way there. So the expectation, the average, that the expectation of x bar seems to indicate that the population average should be close to 0.556. All right. Now on the question, it stated, suppose we know that the population average is 0.54. So okay, that's pretty good then. That's hopeful. What about the median? Is the median a good indicator or a better indicator? How do we know? We check the expectation for its sampling distribution. Okay, so we're going to calculate the expectation of M. The expectation of M. And looking back at the table, so M could be -5 with a probability of 25 over 729. 25 over 729. It could be 0. Well, 0 times the probability is just 0, so I'll put 0 there. Plus 5 times 92 over 729. All right. We go to the calculator again. I have -5 times 25 divided by 729 plus 5 times 92 over 729. I am getting an answer here of 0.460. So the expectation of the median sampling distribution gives us an expectation of 0.460. The population average is supposed to be 0.54, which means X bar has done the better job. X bar is closer to what we're trying to find. Okay? So we go back to the question. How do we answer then? Which distribution is a better estimator for the mean? The X bar sampling distribution is the better one. All right. So if I share my screen again here. And for X bar, it's okay if like you don't have, obviously you don't have a button on the keyboard, which is X with a bar over it, but it's okay just to like type into the answer. You can just say, the sampling distribution of X bar. It's okay just to write it that way. X bar is the better estimator. All right. And that's it. That's all you have to put in for participation day 15, and that will give you full credit for today's participation. All right. So I'm going to go ahead and stop there. This wraps up section 6.1 and 6.2. We're going to cover 6.3 in the next video. And there we'll actually talk about, okay, so how do we calculate probability in this kind of situation? We'll talk about how to determine z-scores, since it is a little bit different in this setting. We'll see that in section 6.3. All right. So that's it for this video. Of course, if you have any questions, concerns, please feel free to email me, come by office hours, let me know. I'm happy to help, talk you through it, try to help figure out what's going on in order for you to better understand the material. All right. So if you have any questions, let me know. Otherwise, best of luck, and I will see you all in the next video. Okay. Have a great day.